The next lightning talk will be Suresh Venkatasubramanian, professor of at University of Utah School of Computing. Suresh background is in algorithm and computational geometry, as well as data mining and machine learning. His interest currently lies in algorithmic fairness and more generally the problem of understanding and explaining the result of black box decision procedures. Suresh has received a career award from the NSF for his work in the geometry of probability, as well as a test of time award at the ICDE 2017 for his work in privacy. And his research on algorithmic fairness is very well known and received a lot of coverage in the scientific literature as well as in the general press. He is a member of the Computing Community Consortium Council of the CRA, member of the board of the ACLU in Utah, and a member of the New York City Failure to Appear tool. I wonder what that is. Research Advisory Council. So welcome here, Suresh.
Thank you very much for having me. Quick question, is there a clicker here? Or just a keyboard? Just a keyboard. Okay. The green button, yeah. Okay. Yeah, so thank you very much for having me. I might be able to answer your question depending on how much time I have. It's a tool used in the criminal justice system here in New York. So I'm a computer scientist, and I'm here as part of your celebration of AI in medicine. But I'm also here to rain on your parade a little bit, to introduce a note of caution into the excitement about the use of AI. Of course, while AI is now sort of rolling out in medicine in a big way, and has been for the past few years, it's also been rolling out in pretty much every other part of our society. And just a few of the many examples of where machine learning in particular has been present in our daily lives in the world we live in ways you may not even realize. For example, in college admissions, there are profiling systems to decide who would be good applicants to admit and what is likely to be the trajectory once they're admitted to college. Whether you want, credit has always been something where we've used data to try and figure out who would be a good loan risk, but this has become even more sophisticated, using things like social media and other factors to try and predict who would be a good loan risk. To get a job, a lot of jobs now have an initial phase where you do an interview, you write down some answers, and there are machine learning systems that process those answers to determine your core competencies and whether you'll be appropriate for the job. A lot of this happens in the national security venue, some of which we know about, some of which we don't. And of course, in criminal justice, in pretty much every way you can imagine, machine learning has integrated within the criminal justice system in ways that are quite startling, all the way from policing to initial pretrial hearings, to sentencing, to parole, to what have you. And because we now have this extensive experience of what happens when machine learning gets thrown into the systems, we also know something about some of the problems. And that's what I want to talk about a little bit right now. One of the most basic problems you have is bias in training, and machine learning in particular relies on lots of data. As we've heard, data is very important. You use data to build predictive models, and if you have problems with your data, you'll have problems with your models. So probably one of the most famous examples of this is an article, a study that came out a few years ago from ProPublica, showing how systems used to predict whether someone will recidivate, commit crime after they've been released from jail was racially biased. There's many things more I could say about this, but in interest of time, I'll move on. Another sort of problem is feedback loops. So, we build these systems, we want to use them, and we're happy to use them. But once we use them, the data that gets generated from the use of machine learning systems, in many cases, gets fed back into the process of learning. And that creates these feedback loops that can cause systems to go out of whack. Another well-known example of this is that in predictive policing, if you have a predictive policing algorithm that tries to decide where crime is likely to be committed, and your system tells you where to go, well, you see crime. And that reinforces what the system is telling you, irrespective of what the actual crime rates might be in different areas. And this is fundamentally a problem of the mechanics of how learning is done. It's sort of both a mathematical problem as well as sort of a more basic problem in policing as well. Models are fragile. This is an old paper, but it's a sort of very entertaining one. The picture on the left is a result of a deep learning system trying to classify an image and saying, with some degree of confidence, that's a panda. And now you apply a small amount of noise to it. So what you would see is the image on the right. But what the system sees is a gibbon with 99% confidence. And again, this sort of is one of those Achilles heel problems where the more sophisticated your system gets, especially with deep learning, inevitably the more fragile it gets, the more sensitive it gets to small perturbations. And those small perturbations can wreak havoc on the system. We've heard of examples where, for example, you can put stickers on a stop sign, and an autonomous vehicle will think it's no longer a stop sign, but a speed limit sign, and will go right through it. So, lest you think that medicine is sort of free from some of these problems, it's not. And there are at least some examples that are both older and more recent. You probably heard of some of these already. The problems, for example, of using automated system to detect sort of signs of melanoma in skin, the fact that dark skin and light skin sort of work differently, and if you don't train your system properly, you'll have problems with detecting melanomas. The fact that we talked about lots of wearables, it turns out that some of the wearables, things like Fitbits, don't work as well on dark-skinned people. So I should have had my Fitbit here today, and I forgot to wear it. I have 9 other devices. Yeah, sorry. but this can be an issue, and maybe one solution is to have so many different devices that it compensates for some of these problems, and that's a possibility. But it's something that we need to be aware of, that these things, and I like the idea of individualized baselines because it takes away some of these issues there as well. Also, this is actually a very recent paper, an interesting problem of what the authors call hidden stratification that again relates back to the issue of training, that depending on what kind of training data you have and what kind of subtle variations there are in the training data, you might pick up different kinds of patterns which may or may not be accurate for the problem you're trying to solve. So there's a whole area that has grown up over the last 5 to 10 years around this area. I mean, it's roughly called fairness, accountability, and transparency. It brings together people from computer science, sociology, law, economics, philosophy, policy, and ethics. I'm teaching a class on ethics and data science right now in my computer science department, which is very unusual for a computer science department and makes the students very concerned. And science and technology studies. Medicine is, of course, has been part of the push. The revolution in AI has not as much been part of the push for discussion of the sort of the limits of AI, and I think that's something that hopefully we can talk more about today as well. There's even sort of a conference around this. This is a computer science thing, so we do things in conferences because we like to be different, and there's a whole event that is organized around these things. And in the few minutes I have left, what I want to tell you about is some of the things that people are beginning to think or have been thinking about now for a while in trying to deal with some of these problems. So in other words, I don't want to merely tell you that, oh my God, there are problems, you can't do anything about them. There are actually many things we can do about them, and we're thinking about how to do them. And that's what ongoing research is, and that's what makes this area very exciting right now. So for example, the problem of dealing with proxies, right? So there are features that you may have that are correlated with predictive features like race, gender, sexual orientation, especially in certain settings. This is a very big problem. And then you want to be able to retrain your models appropriately. So, example of you don't want something like this to happen, where basically, and this is, very recently, maybe a few weeks ago, there's a passport photo check system in England, and a man goes up to get his automatic passport photo taken. And it says, no, your picture is wrong because your mouth is open. He just happens to have thicker lips. And these kinds of systems are things we don't want to have happen. And it's also an illustration of how proxies can be very subtle, right? So you can have a system that collects a lot of data, and you think all this data is more or less neutral, but there's some proxies that can be predictors for something other than what you're trying to predict for. They could be predictors merely for socioeconomic status or other things. And this can cause discrepancies for different groups in a population, and that's going to be a problem for you. You want to deal with representation bias. One of the sort of secret things about most machine learning systems is that they're not just doing prediction, they're actually building abstract representations of you by collecting data about you and building it into some kind of general framework. And if those representations themselves have bias in them, it doesn't matter how good your inference procedure is. It will only carry that bias over into the inference. And so we've seen examples of this already. We've seen this, for example, in natural language processing in text, where text can carry biases, in this particular case, gender biases, into the text. This is particularly relevant, for example, if you're dealing with electronic health records. I have colleagues who are looking at exactly this problem of how biases might creep up in doctors' notes, and again, as a text format, and how that might affect sort of the way in which these health records are interpreted. Again, in images, there's a very famous study from a few years ago on how facial recognition systems do very badly on, say, gender identification for darker-skinned women. And in general, facial recognition systems have discrepant behavior on different groups of people. This again is an example of how image processing can itself can create biases in a certain way. Finally, fundamentally, and I think this is of particular importance in medicine more so in other areas, what you really want is to explain the predictions that a system is giving you. You'd like to understand why the system is doing what it's doing, because you want to use this notion of augmented intelligence that I think you mentioned earlier, that you want to have something that augments the doctor's sort of knowledge about a situation. And so in that case, having a system that says, well, I predict that this is a particular outcome, or this maybe indicate a higher, an elevated diabetes risk, you'd like to know why. You'd like to know what factors in the input are contributing to this. And again, this is something where people are beginning to look at this problem. For example, if you take an image and you want to say, this is an image of a vase with lemons, you'd like to say, okay, what made you think that there's a vase in this picture? And then the system can actually say, no, I looked at, on the right side, the top of that thing, it looks like the top of some kind of cup, and that's why I think it's a vase. Now, I'm paraphrasing what the system would tell you, but the efforts around explainability, I think, are very important in this setting because you'd like to understand what these systems do. And with that, I'd like to thank you all for having me here. I'm a computer scientist. This is not a place I'm normally used to being, and I'm thankful for the audience.